Hello everyone, so this is a little summary of solving trigonometric equations and then we'll move on to triangles and cosine rule. But to begin with, we'll do this by an example because really and truly, you could be looking at the steps all day and they mightn't make any sense unless you have an actual equation to look at and understand. So if you're asked to solve cos of 2 theta equal to 1 over root 2, where theta lies between 0 and 2 pi, this is actually giving you information. It's telling you that your answer must be in radians and your answer must be at most 2 pi. You don't go beyond 2 pi. Okay, very typical trigonometric equation question where they ask you the cos of 2 theta or sine or tan, or 3 theta. They haven't quite gone to 4 theta. They've done an odd theta over 2. Okay, so I'm following through here and the steps go 1, 2, 3, 4, so they go down and then they go up. So the first step is to find an angle, and you do that by getting cos inverse of the right hand side above 1 over root 2. Now, if you want to give your answer in radians, then turn your calculator to radians to get out the answer of pi over 4. Students often ask me, can I do it in degrees and then convert back to radians at the end? You can. It would be slightly preferable, just because of rounding errors, it would be preferable to do it in radians, but you can absolutely. Okay, as long as you just make sure at the end, if you're going from radians to degrees, don't take the approximation at the bottom of page 13. There's an approximation there where 1 radian is approximately equal to whatever. Say, for example, you have pi radians, you want to get to degrees, multiply by 180 over pi. That'll get you the exact amount of degrees, actually. And vice versa, if you're going from degrees to radians, multiply by pi over 180. Anyway, sorry, I digress. So you get cos inverse of the right hand side to give you an angle, okay? Then step 2 is you find the quadrants where cos is positive, because we're trying to solve cos 2 theta equal to 1 over root 2, which is positive. So CAST, this is where cos, all, sine and tan are positive, so we want the bottom right and top right, okay? From there, we find the second angle. So this is step 3 over here. We use pi over 4, which we got out of our calculators, to find the second angle in the cos plus quadrant, okay? And when you're looking for that angle, you use pi over 4 and you use it to measure up and down from the x-axis. So if you need to get into another quadrant, you always measure up and down from the x-axis. So we come down from the x-axis by pi over 4 to get down into this bottom right-hand corner. But remember, we always measure angles starting at the positive x-axis and going anti-clockwise. So the black angle there is 2 pi minus pi over 4, which is 7 pi over 4. So now we have two angles, pi over 4 and 7 pi over 4, okay? And we know, so next we want to find theta. So we get theta by knowing that 2 theta is pi over 4 or 2 theta is 7 pi over 4. But because we're solving for cos of 2 theta equal to 1 over root 2, if that number in front of theta is anything other than 1, add 2n pi, that adds all extra rotations. So 2 theta is equal to the angles we found plus 2n pi. And then we know that it's theta we're looking for, not 2 theta, so divide across by 2 to get theta equal to pi over 8 plus n pi, or 7 pi over 8 plus n pi. So we're both dividing both terms by 2. And this is the point then when you let n be 0, 1, 2, etc. and stop when the solutions go beyond 2 pi. That's because of this constraint here. So n equals 0 gives us these two, n equals 1 gives us these two, and you can see even if you let n equal to 2, already this quantity here would be n equal to 2, this one down here, there we are, would already be 2 pi, so we'd know our answer had gone beyond 2 pi. Okay, so that's the structure. They are the 5 steps. You find your angle, you use CAST to find the second quadrant where your angle solution might lie. You find your second angle, you find theta, you let n be 0, 1, 2 and 3. Now variations on this are as follows. If you are asked to solve the same equation but theta lies between 0 and 360, that's telling you to give your answer in degrees. And the only difference in all of the steps below is instead of adding 2n pi, we add 360 degrees n. Okay, and then another variation is if you were asked to solve cos of 2 theta equal to 1 over root 2, where theta is an element of the real numbers. That's asking for all possible solutions. There is no constraints on theta. We don't start at 0 and end at 2 pi. We let theta run through all real numbers. First and foremost, radians are real numbers. So you'd find your answer in radians to begin with. And then you give the general solution. So you stop before letting n be 0, 1, 2. So we stop at this point here. Sorry for all the red circles. The solution is theta equal to pi over 8 plus n pi, 7 pi over 8 plus n pi, where n is an integer. Okay, so that's solving trig equations. And then moving on to what you need to know about triangles. So I've broken this into the green box on the left, which is right angle triangles, and the pink box on the right, which is non-right angle triangles. Now, all of this information is on page 16 of your log tables. When I say all of it, most of it bar the bit where I say you should use this in this scenario, So right angle triangles, there isn't a huge amount that is new here on the left-hand side. If you have right angle triangle, Pythagoras theorem, sine theta, cos theta, tan theta, they're the only things you know about right angle triangles. Everything you knew from junior cert, actually. The good news about the right angle triangles is that for the 3D problems, most things point out of the ground at a right angle. A pole will be perpendicular to the ground, etc., etc. So you often end up using right angle triangles, or you're encountering right angle triangles in 3D problems, and they're not the worst in the world. Pythagoras, sine, cos, tan. Use sine, cos, and tan if you're given an angle and you're looking if given an angle or you're looking for an angle. Yeah, if there's mention of an angle, use sine, cos, or tan. If it's only relating to, say, the side lengths and you have two sides, you need a third, use Pythagoras theorem. So the first question you should always ask yourself with a triangle is it a right angle triangle? Then you're in the green box. If it's not a right angle triangle, you're in the pink box here on the right. So non-right angle triangles. Okay, what do we have? We have the blue arrow coming out here, which is the sine rule. Sine rule is on page 16 of your log tables. But what's not there is when you use it. Use if you have a lot of opposite information. You can see with the sine rule, you have A over sine A, B over sine B, etc., etc. So here in this example, lots of opposite information is given to us. One piece is unknown, the x, so you use the sine rule to solve for x. Okay. Also with the sine rule, you only ever use two of those at once. You never set up the three equalities. Then the pink arrow here down to the cosine rule. Cosine rule is also on page 16 of your log tables. Something that is confusing with the cosine rule is to know which side goes over here on the left by itself. It is the side opposite the one angle that appears in the formula. There's only one angle in this formula, and the side opposite that angle is all the way at the opposite end of the equation. And then the two sides on the inside are B and C, the other side of the triangle. When do you use the cosine rule? So you want to kind of be prepared so that you can jump kind of straight to using the rule you should be using. So you should use it definitely if you're given three sides and looking for an angle. That's the only rule to use, it's the cosine rule. Or if you're given two sides and looking for the in-between angle, generally you'd use the cosine rule. Sometimes you can use sine rule in that instance too. And there's a little example, given three sides looking for an angle. And 13 is opposite theta, so 13 is on its own there and theta is on its own over there. And then finally, for a non-right angle triangle, on page 18 or 16, we have a formula for the area. It's a half AB sine C, which is a half one side by another side by the sine of the in-between angles. So if you have, for example, A, B, and there's C, and there's C, and A, and B, it's a half A by B by the sine of the in-between angle.